Good morning, everybody. And I'd like to give you some ideas this morning about how to use the awesome structures that you can get from AlphaFold and the other advanced AI methods. Now, as the title suggests, AlphaFold and other AI methods, I'll use AlphaFold generically for all these methods here. They've already transformed structural biology. But in a way, nothing has really changed because the experiment is still crucial. Now, with your help, I'd like to prove this right now. So, how many in the room have solved a structure with X-ray or cryo-EM in the last 2 years using an AlphaFold or other AI model? Raise them high. Yeah. Okay, great. That's part one, right? So AlphaFold changes everything, right? So now, raise your hand again if your experimental data told you something that that AlphaFold model could not tell you. Thank you. Proof number 2. Okay, so the experiment remains crucial. So AlphaFold models, AI models, they're great hypotheses. So if you listen to nothing else I say during my talk, just go home with that message. They're hypotheses. They're great hypotheses. Use them like hypotheses. You can use them to plan your experiment. Where are my domain boundaries likely to be? So where might I cut when I'm going to design my constructs? Use them to solve your structure. And I'll show you about this today. You may not know it yet, but you can get improved predictions with AlphaFold using your structure as a template. So you can then improve your structure and iterate that process. So let's talk for a moment about the information that goes into the training and application of a procedure like AlphaFold. So training, what goes in? Sequence for each structure, a multiple sequence alignment for each structure, and a three-dimensional structure coming from the protein data bank. 180,000 protein structures in the PDB. Wait a minute. 180,000 structures in the PDB, where did they come from? Us, right? We did that. So give yourself and your colleagues a hand for solving those 180,000 structures that made AlphaFold possible. That's us, and 60,000 depositors did that. And it's awesome, right? This is one of the best databases in the world. It's a structured database. It has all of our important data in it in all the same way. It's perfectly set up for something like AlphaFold training. So be happy about that. We made that possible. And now I'm going to show you in the rest of the talk how we can take advantage of what we made possible. Okay, so AlphaFold generates 21 million parameters that allows it to predict the structures of proteins from the PDB using these sequences and multiple sequence alignments. So now you come in with a new sequence and a new multiple sequence alignment. AlphaFold takes those same 21 million parameters, applies them in exactly the same way that it did in training, focusing attention on important relationships, and comes up with a three-dimensional prediction. And you'll notice that the prediction and the structure don't look exactly alike, but part of it's very similar. I'll actually use this example throughout my talk. And very importantly, AlphaFold predictions come with confidence estimates. Confidence estimates residue by residue. This is one of the most important aspects of this whole prediction process because the confidence estimates are not perfect, but they're pretty good. And so you can identify what parts are good and what parts are not likely to be good and whether the whole thing is going to be useful in advance. It's really awesome. The multiple sequence alignment is key information for AlphaFold. So just to remind you, a multiple sequence alignment is a list of sequences that are aligned to each other using some procedure or another, where it's thought in this sequence alignment that residues that are one above the other correspond to each other in a structure, and all the structures in a sequence alignment are somewhat similar. The key ideas are that residues that co-vary, that is, change together when in different sequences, in different species, are probably close in three-dimensional structure, at least more likely to be close than other residues. And this has been shown by many people, but it's key information because if you find residues that co-vary, that means they're probably close, and therefore in the prediction they ought to be close. It's like a distance restraint. Another aspect of the multiple sequence alignment that's not really well appreciated is that all the sequences in the alignment should be more or less compatible with the same structure. That means that all those different mutations that are in that multiple sequence alignment ought to be more or less compatible with the structure. And we actually don't know exactly what AlphaFold does. It's opaque, right? It's a neural network, 21 million parameters have never been analyzed to figure out exactly what it does. So it's conceivable that neither of these things is even used by AlphaFold, but it's not likely. It's much more likely that it figured out how to do these two things. Okay, so a consequence of the sequence alignment and multiple sequence alignment idea is that if you have a lot of sequences that are related, then you may have more information about what residues are close. So in this picture, the left-hand side of this molecule has high sequence coverage, and the right-hand side has lower sequence coverage. And correspondingly, the left-hand side has higher confidence, and the right-hand side, more or less, has lower confidence. So predictions often are accurate where the sequence coverage is high. So here's an example I'll show you a few times. This is one chain, chain H, from a structure that has multiple chains in it. And we're just going to box out this chain from a cryo-EM structure and look at what its properties are. So the pink here is the deposited structure. The green is the AlphaFold structure. You'll notice that part of it looks very similar, at least superficially, as a main chain tracing. And part of it doesn't look all that similar. In fact, these are the parts that have high sequence coverage and low sequence coverage, as I mentioned a moment ago. Let's look at this in more detail. This is the awesomeness of AlphaFold predictions. This is the high confidence part of the molecule, residues 1 to 100 of this chain. And it's not perfect in that it's not exactly the same as what is in this structure, but the prediction is amazingly similar. And a few years ago, if you got a structure that looked like the green one and you really wanted to get the pink one, you would say, I got it. Right? So this part of it is extremely similar. It's extremely good. Not every side chain's in the right place. So high confidence residues can be very accurate. But know that local accuracy, which I just showed you, is very often better than global accuracy. So here's a prediction of a domain 3 of chain A of PDB entry 7 BGL. It's a 26-mer. And so a little bit of a challenge. So we predict this with AlphaFold, and what do you get? It's a little bit of a mess. But actually, if you look at it in some detail, there's the mess. There's overlapping. But if you just look at one monomer, it's not perfect, but it's actually quite similar to the right answer. So what's happened here is that there's long-range distortions. And that's because AlphaFold doesn't really know much about long-range interactions. There isn't much information coming in to tell it about that, and it tries to pack things close together. And actually, it doesn't even pay attention, in fact, to very long distance relationships. So that's why it can make a tangle like you see in the bottom. So AlphaFold structures are great hypotheses. Now, some limitations. Well, it's only protein, and it's no environment, right? The environment's not included in these predictions. Hint, hint, those of you who are going to do the next generation, well, think about it. Okay. So no water, no ions, no covalent modifications, no carbohydrates, no ligands, RNA, DNA, and no environment-dependent conformations. All right, well, what else do we do? Yeah, okay. So, and it's trained on good and poor structures. So this is a easy limitation to get around. So AlphaFold, they just took everything, better than 9 angstroms, and just threw it in there. So there may be some things that are systematically wrong because they didn't include just the good ones, or the good parts. And it's trained to match the PDB. So the right answer for an AlphaFold prediction is what would get deposited in the PDB if somebody solved this structure. That would be the best possible answer that AlphaFold could come up with. And so anything that's not going to get deposited in the PDB, like intrinsically distorted regions or something like that, you're not going to get any information about that. Okay. And as I mentioned, there's little information about residues that are far apart, so you get distortions and incorrect domain relationships can happen easily. Okay, so AlphaFold changes everything. Let's come back to what you guys already showed us in my first slide. Let's talk about using AlphaFold hypotheses to solve your structure. And I want to give you some ideas about how to do that effectively. So here's just a generic process of doing that. So here's an AlphaFold prediction for 7OA7. Is that anybody's in this room? I don't know. Okay, anyways. Thought it might be. So high confidence is red and low confidence is white or blue. Okay, so this is what you get as your AlphaFold prediction in the beginning. And so you can color code them by confidence. And so what are you going to do with this? Well, I think what you're going to do is the parts that are really low confidence, you're going to get rid of them because at this level, it's not going to help you at all. You want the high confidence parts. And then you notice that if we trim the blue and white, then the red actually looks like two domains. And it's probably a good idea if just like have one teeny linker between them, maybe you would chop this into two domains to do whatever you're going to do next. So fine, let's do that. And then this is a crystal structure. So take those two pieces and do molecular replacement with them. What do you get? So here's what you get. And you notice actually it was pretty close. They have a slightly different relationship than they did in the predicted model. So it was a good idea to trim it. But basically, it's not bad. Okay, so now if we just look at the density that comes out of doing molecular placement, the right-hand side there looks pretty good. The left-hand side, some of it's okay. The middle, some of it's not so good. You can just refine that a little bit. Didn't do much. But this is a high-resolution map, right? And so you can just rebuild this. And this is what you would do. You just throw it into ArtBorp or AutoBuild or some program that does that. Rebuild this thing. Poof, you're done. Okay, you're done. That was it, right? All you did was you did a prediction. You trimmed off the bad stuff. You cut it into domains. You did a molecular placement. You refine it a little bit. AutoBuild. You're done. Okay, so those of you who have used AlphaFold models, you may have had such a nice experience. If you had low resolution structure, not so easy, of course. A lot more to do. But that's the basic thing, is AlphaFold jump-started this whole thing, right? You didn't have to find a homology model that wasn't all that good and figure out what the right sequence alignment was and everything. Boom. It's just, you're right there. Okay, so very handy. Works great, particularly for, if you have a good prediction, most of it is good and high confidence, and you have good data, you're in really great shape. So be happy. Okay, so is this a typical example that I just showed you or not? So we wanted to answer that question. So what we did was we said, let's go and look at harder structures. And how do we find harder structures? Well, not in any good way, but we thought, let's just go and take all the structures in 6 months that were solved by SAD phasing. So probably those were structures mostly that they couldn't solve with molecular placement, so they're a little bit harder. And so let's try to see what fraction of those we can get just by doing the absolutely straightforward thing like I just showed you. Okay, so it turns out in 6 months there were 215 unique structures that had these characteristics that contain protein. So you gotta have protein or else it's not gonna work, obviously. Okay, so we do AlphaFold prediction, split them into domains, solve the structures from molecular placement, and rebuild automatically. So everything's totally automatic. We didn't do anything by hand here whatsoever. So what's the answer? So here are the free R values for those 215 structures. 7 are not shown because they failed molecular placement when I was doing it. So 0.3 here, let me just get my mouse. All right, so if you run an AutoBuild or ArtBorp job you just get out of it a free R factor of 0.3, you're very happy. It's like you haven't even put in waters, no ligands, you haven't finished everything up. It's good, right? So all those are fine. These others here, in fact, all the black ones are good, and the ones that are open circles are not good. And so a very high fraction, you can see, are pretty good. So let's quantify that. So we take all the structures, and we ask what fraction of them had a map correlation to the deposited model. So we calculate a map from the deposited model, have our map, and we do the correlation between those. If it's bigger than 0.2, which basically says there's some correctness to it, it's not totally random, 90% of them have that characteristic. Okay, so now let's break them down. Well, what about those that had low confidence? So there were 10 structures that had confidence, PLDDT is the acronym for this, under 70, so not that confident, for at least 50% of the residues. So basically, these are not that great predictions, and only 10%, i.e. 1, of those worked. And then of the others that had at least PLDT of 70 for at least 50% of residues, 94% just went right through. So this was pretty good, and actually, it's even a little bit better because I used, sort of totally generic molecular replacement things for this, and Airley's redone it, and almost all of them work, in fact. So it's even better than what I'm showing here. And these numbers actually make a lot of sense. So PLDDT of bigger than 70, that actually translates into an RMSD of about 1.5 angstroms for 50% of residues. And actually, just think about it, what's our sort of rote idea of what's going to work for molecular replacement? Well, if it's like 50% of the residues are within, about 1.5, maybe 2 angstroms, I ought to be able to solve it by molecular replacement. That's just what we've been talking about for 20 years. And that's exactly what the answer is here. So it's exactly the same thing. So great. And the good thing is the confidence measure is actually pretty good at telling us whether that's going to be the case. So we're good. All right. So AlphaFold predictions, they're great for jump-starting structure determination. And the confidence measures, they allow pruning of the worst parts of the models. The confidence measures are often accurate. It's better than a homology model because there are no insertions or deletions in the sequence. And the high accuracy of entire domains helps structure solution. It's a little bit subtle, but in molecular replacement, the key thing is how big a piece do you have that has very high accuracy or is very close to the right answer. The bigger the piece, the more accurate, the better molecular placement is going to work, and AlphaFold domains are perfect. Okay. So can AlphaFold predictions help if the structure is already solved? So I'll show you a real case here that it did. So here's this is the DNA, RNA part, the protein part of a repressor DNA complex. So solved at 2.6 angstroms with SAD data, refined against 3.1 angstrom native data. This is Jamie Wallen's work. He sent us this structure a couple of years, actually too early. We couldn't do anything. And then after AlphaFold came out, we were able to help him. So here's his problem. He's able to build what you see here. And here's the density that goes with that. And the question is, how do you connect up these two loops? Where does it go? And I challenge you to really see what's supposed to happen here. But AlphaFold gave us a great hypothesis. So here's this. We put in the whole entire sequence of to AlphaFold, and there's the AlphaFold prediction. Wow. Notice that the part that we knew is right, and not exactly, but pretty much right. And then it gives us a hypothesis of how to connect these guys up. And it's like a totally plausible hypothesis, right? It's just, oh, wow, it just makes like a little beta strand here, and everything hooks up great. And then we look at the density, and you couldn't do any better than that, right? So now you refine this, and the R factor goes down from 2729 to 2124. It's obviously correct. Okay, so what happened? We used AlphaFold to generate a hypothesis. We tested the hypothesis. The hypothesis is obviously correct. right? And now we have an answer. So AlphaFold can help you even after you've done most of your work, yes. So now I want to tell you something new. Actually, I need some help, Diana, because I don't know how many minutes I've used.
20.
Perfect. Okay. So, yes. So here's something you don't know, that you can use your working model to get a new AlphaFold prediction. And that new AlphaFold prediction can be better than the one you started with. So you do your AlphaFold prediction, you solve your structure, you get yourself a working model, and then you generate a new prediction based on that working model. And so the amazing thing is that the new prediction may be better than the original prediction. It may also be better than your working model. And I'll show you an example of that. In fact, we had a Phoenix workshop yesterday, and the participants solved this structure that I'm showing you here, and they could see, in fact, that it was better than the working model that they had. Okay, so let's see about that. This is the same one I showed you earlier, where part of the structure has high sequence coverage, and part of it has low sequence coverage. There's a little bit more to it. This part of the model, of the molecule, actually is in contact with another molecule here too. So there's more than just the fact that there's sequence coverage in one part and not in another. Okay, so we're going to look now at this junction here between the part that's good, that's high confidence and correct, and the part that's bad, that's lower confidence and actually not even plausible configuration. So here's the density that goes with that. So the left-hand side is the good part, high confidence and correct. The right-hand side is low confidence and not even correct. So that's the AlphaFold prediction. So now we throw away the part that doesn't fit the density and just use typical model building tools to rebuild the loop. And there's the part of the rebuilt loop. It's not the greatest rebuilding or anything, but it kind of shows AlphaFold where to go. And then we use this as a template to tell AlphaFold where to how to build the model. I just want to note that AlphaFold allows you to choose templates from the PDB in prediction. That's part of the standard procedure if you want to do that. So this is using the same ideas except supplementing it with our template, not something from the PDB. So now we use this as a template, and there's the prediction using that as a template. It's a little bit closer. And notice that to rebuild this doesn't really take much, right? You're just going to flip that tyrosine up there, move the main chain in a little bit into the right position. So this is rebuilding the next cycle. Now we use this as a template, and there's the AlphaFold prediction after it sees that. So basically what AlphaFold is doing is when it recognizes something is good, it takes it. That's basically what it's doing. It's using the template we provide to give it ideas about what's close to what. And then if the template has good features, it takes it. If it doesn't have good features, it doesn't take it. So after a couple cycles, the template is very similar to the prediction, and both are very similar to the right answer, the deposited model. Okay. So you can do this in crystallography as well. So that was cryo-EM structure. This is the same structure I showed you earlier, 70A7. This is the model from molecular replacement, which fits the density quite well. So this without doing very much. After rebuilding it, so rebuilding it adds more residues and adjusts it to match the density. There's the next level prediction, and it's not quite right. You can see it's distorted a little bit. This is, as I told you, is fairly common in AlphaFold predictions that there may be systematic distortions that are long-range distortions. And so it doesn't fit the density so well. But if we refine that in, rebuild it, and then predict again, using that one as a template, it's much closer. And after a couple cycles, in this case, the AlphaFold predictions are basically spot on. So here's the AlphaFold prediction in cycle 5 of doing this, superimposed on the deposited structure. Looks just like it. So does this always work? Well, so here's a plot showing for all the ones we tried how that works out. So the x-axis, those that are above the line, the initial model, the first AlphaFold model was better than the last AlphaFold model. Those that are below the line, the last AlphaFold model is better than the first one. And so they're, it's not always better, but often it is. So that gives you an idea that it's worth a shot, particularly since this whole process doesn't take all that long and is pretty easy for you because the software can do it for you. So why not? So another thing you may or may not know is that AlphaFold predictions often, not always, but often have excellent geometry in that they have Ramachandran characteristics that are better than we can build. So here are models that we've auto-built with our tools in black, and the AlphaFold models have a higher fraction of favored Ramachandran values, and similarly the outliers, we have more outliers in our auto-built models than the AlphaFold models. What that means is you can take advantage of AlphaFold models as reference models in refinement, using them as a guide for what the backbone angles are likely to be that may be better than the ones that you can get by auto building. So now I want to come to the other side again and ask, so how accurate are AlphaFold predictions? What can you really expect to get out of this? And so this is the cautionary part of this, and I want to emphasize that the use of these confidence metrics is a really powerful thing in evaluating accuracy, expectations of accuracy. But so let's compare AlphaFold predictions to the deposited models, and let's ask how similar they are. And then as a reference, we're going to use comparisons of pairs of structures of the same thing that are deposited in the PDB that were in different space groups. The reason to do this is that if you take the same thing and you crystallize it twice in different space groups, they're going to be a little bit different. They're going to have different crystal packing, probably a different pH. Things are a little bit different. And so how different do we expect things to be that really are what we think of as kind of the same, right? And of course, some of these might have really big differences, and we'll notice that. Okay, so that's going to be our comparison. So we want to know how the differences between AlphaFold models and deposited models, how do they depend on confidence, and how much of the difference, importantly, is going to be distortion that I've mentioned a few times, or domain movement, and how much of it is like local actual differences where the structure really looks different. So we're going to try to look at those different things. And as I said, we're going to compare this with matching high-resolution structures from the PDB. Okay, so let's do this. So we're going to look at overall differences, just superimpose the deposited model and the AlphaFold model, and just compare C alpha positions. How different are they? And then to get local differences, we'll take the AlphaFold model and we're going to morph it. We're going to apply a systematic a deformation to that model that has a characteristic distance, a smoothing radius of about 15 angstroms. So basically, things that are closer than 15 angstroms won't change much. Things that are more than about that will start changing. So we'll distort the one model to superimpose on the other, and then we'll look at the C alpha differences of that and see how different they are. Okay. So, and then finally, we're going to compare these high-resolution structures. So we found 922 pairs of structures in the PDB that are unique, that have exactly the same components. That is to say, if they have the ligand, they have the same ligands. If they whatever proteins are in there, the same chain, same number of chains, all that kind of stuff. So they're identical, large-scale components. If there's a duplicate of, if there are more than two space groups like lysozyme or something, we only took one, right? So there's 922 of those that are better than two. Everything's better than 2 angstroms. So this is like kind of the ground truth of what you expect. So this is going to show it. This is what may vary in a crystal structure. Okay. So, oh yeah, I didn't mention that we skip the residues that are at crystal context. So just so we're not even thinking about that, we're going to take that off the table. So the residues that are actually at crystal context within 6 angstroms of, crystal, of something in the other chain, we're just not even going to consider it. So you don't have to worry about that. Okay, so here's the answer. So we take so we do all these things, we superimpose all the C alphas of AlphaFold models onto the top of the PDB structures. And we look, and then we look at the C alpha distance differences. And first, let's look at the differences for the PDB matching structures in the space group, in different space groups. So that's the big dotted line there. So the median difference in locations of C alpha atoms between two pairs of superimposed matching structures, median is 0.3 angstroms. And yeah, I see some nodding, like that's what you expect, right? So half of them are better than 0.3 angstroms. So that's kind of the end of my chart here. So these are very good. And of course, there are some that are longer, that are farther off, and that's because there are some domain movements in these cases too, right? So it's not like perfect or anything. All right, so now let's look at AlphaFold models. So PLDDT greater than 90, those are what's considered very high confidence predictions. So this is like the highest category of AlphaFold predictions. And actually, most AlphaFold predictions are in this category, in fact. But this is ones that are thought of as very good. And so they have a median of 0.6 angstroms. So this is very good, right? It's very impressive. But it's not as good as pairs of structures that are identical, in fact. So it's twice that. And once you fall off in confidence here, the ones that are 80 to 90, so that's a median of 1.1, so it's twice as big. 70, 80 is 3 times as big, 1.5. By the time you're below PLDT of 70, so this is lower confidence, but not considered to be zero confidence. So now the median is 3.1 angstroms. So basically, these parts of predictions or these predictions, they're useful for something, but in terms of identifying what's in contact with what, not so useful. And now, what about, this is without doing the morphing. So this is just superimposing as is. What if we morph and ask what are the local differences? And it's actually very similar, except most everything is a little bit smaller. So now, the ones from the PDB are now 0.2 angstroms. The PLDDT greater than 90 are now 0.3. And so everything is just scaled down a little bit. So about half of the differences are local, half are global. Okay, so here's a handy little chart for you. So you can memorize this chart. It's not very hard to memorize, as I'll show you in a second. You only need to remember one line and one ratio. So here it is. If your AlphaFold confidence for this residue, not for the whole thing, for this residue is bigger than 90, half of the time, your residue is going to be, if you superimpose your structure on the right answer being deposited in the PDB, it's going to be about half angstrom off. Half the time, at least that good. But then, about 10% of the time, it's going to be way off, 2 angstroms or more. So these are the only things you need to remember. And then if we go down 80 to 90, the median prediction area is just twice. So it's 1 instead of a half. And 20% are now over 2 angstroms. And if you go down another notch, it's 3 times bigger. 1.5 RMS, a median prediction error, and 30% are more than 2 angstroms off. And if you're less than 70, then a lot of them are more than 2 angstroms off. Okay, so pretty easy. So just remember, the very high confidence AlphaFold predictions, about half an angstrom off on average. And not on average, I didn't want to say that, median. Because the distribution is not normal at all, right? So it's half of them are better than half an angstrom. The other ones are spread out over many, many differences. And 10% are worse than 2 angstroms. And then it just goes proportionally. Keep that in mind. So even the very best are awesome. But even the very best have things that are going to be different from what your structure is going to look like, just like you guys said earlier. Okay. So bottom line here, how does it depend on confidence? We just saw that. High confidence, RMSD half an angstrom. Low confidence, RMSD 3 angstroms. About half of the differences are local, half are global. And it's about twice, the best AlphaFold model predictions are about twice the errors of differences of pairs of matching high resolution structures in the PDB. That's it. What about side chains? Well, actually, AlphaFold side chains, they're actually predicted kind of as an afterthought. You predict the whole thing, all the main chain and everything. And then at the very end, there's like another little module that just like tacks on side chains. And so you don't actually expect them to be so great, but they're pretty good. But here's one where it's not so great. So here's a deposited model, and this part of the structure has some nice salt bridges and stuff like that. And they're supported by the density, everything looks cool. And you do the AlphaFold prediction for the same thing, and it's actually not a bad AlphaFold prediction, but the side chains, they don't know anything about salt bridges. They don't know anything about hydrogen bonds or anything like that. And so they're not in the right place. So just be aware that the side chains may be good, but they may not. And they're not like the thing that AlphaFold focuses all its effort on, so you don't expect so much. Okay. So how are you going to solve your structure now in the AlphaFold era, right? So predict your structure. So predict your structure when you're thinking. Before you write your grant application, predict your structure, right? Because it's going to tell you, it's going to give you ideas, and it's going to give you confidence estimates about those ideas. And so why not, right? Use them to tell your grant committee what you can know today, and actually use them, more importantly, to tell them what you can't possibly know today, right? So you can do these predictions, and you can say, these are my predictions, but my predictions don't tell me anything about what I'm really interested in, which is this, right? Or, maybe it tells you the whole answer, in which case you don't need the experiment, but that's pretty rare, right? It's rare. So don't worry about that. Okay, so design your experiment based on those predictions that you did. It may give you some ideas that may be very helpful. Solve your structure. Choose your method based on what you know at this point. Do cryo-EM, X-ray, molecular placement or docking, whatever. And then, like I told you, update your prediction once you've got your model, run it with your best model, improve your structure, use these new predictions and hypotheses, iterate that process if you want. You can do it by hand, you can use automated tools to do it, however you want to do it. So it's a straightforward procedure now, and AlphaFold has made it much easier for us to do the things that we really want to do. Okay, so where are we going? And where are we? So today, it's awesome. AlphaFold generates great hypotheses. Of course, remember again, where did these hypotheses come from? They came from our structures that we solved, 60,000 people, 180,000 structures deposited in the world's greatest database, and wow, so we made it happen, so we should be happy that we're taking advantage of all this, right? So they're great hypotheses. Experiments are clearly still needed to see the details of the interactions. So it jump-starts it, it gets us going, gives us a lot of ideas, but we need the experiment to tell us what's happening in our case, under the environmental conditions of whatever we're studying. So a couple years from now, it's going to get better, because it's going to be basically a retraining process over the next couple of years using similar tools that are already existing, but better databases, choosing the databases in different ways, partitioning them differently. Should be able to get better interactions. The RNA predictions should be improved. So bringing in another whole class, multiple conformations may start to be addressed in a much more serious way than it is today. So that it's done a little bit ad hoc right now by just sort of chopping out multiple sequence alignments, trying to get a different version. But I think that can be done much better. 5-year time frame, different story. 5-year time frame, we should be able to integrate the experiment with the prediction. So we should have, instead of like running our software to solve a structure and running AlphaFold to do the prediction, those should be one thing, right? You should be feeding your data into some software, and it's going to do prediction, and it's going to do analysis of the structure. It's going to do analysis of density maps, how to build the model, how to put it all together. It's going to do that as one step instead of like doing it as separate steps. That's going to be a totally new thing. It's going to be really awesome. I think it's going to be incredible. That's going to help us with large complexes, rapid structure determination, and ligands and conformations are going to be coming into that story as well. And frankly, this is going to be great times for structural biology. This is going to be awesome, right? Because we're going to be able to do the experiments that we want to do even better. We're going to interpret them as well as possibly can be done, and it's going to be done quicker than we can do it today. So AlphaFold and AI is going to make it great, and this is the time frame that is going to be really, really awesome. In the longer time frame, it's even going to be better. It's going to take a lot more work. I see it as an integration of molecular dynamics, experiments, and prediction. All this is going to be put together into one set of tools. We're going to have basically end up with high accuracy, experiment-guided prediction of detailed conformations and interactions. And that is also going to be an awesome, great times for structural biology. So I'm looking forward to all this, and I hope you guys are too. And thank you very much for your attention.
Thanks for the plug to the PDV, appreciate it, and thanks to the 60,000 people who've deposited data over the years. You didn't say anything about tomography and solving structures inside cells, and I'd be curious about your thoughts.
Yeah, tomography is the natural extension of all this. Tomography is already moving in the same direction of generating relatively high resolution structures. The more that can happen, the better. You know, the tomography, of course, the limitation is that you can't put as many photons or electrons or whatever into the same volume as you can in a cryo-EM or X-ray structure, because you get the duplicates in cryo-EM or single particle cryo-EM or X-ray. But you get to average in tomography, and I think that's going to be very powerful. Basically, our software can do that in a very simplistic way, but later generations of doing that kind of thing will do any kind of averaging necessary and prediction that's necessary. And you know, you're going to be able to take a picture, more or less, of some complex mixture of a lot of things, and you have an idea of what might be in there, what thousands of things might be there. You're going to do predictions of all those structures, right? And then you're going to figure out which one is which, and the whole thing is going to be done as a big complex, right? So it's going to be really awesome. Yes, Stephen, it's great.
So we have a lot of time for questions. Young man over here, please stand up and direct your questions to the audience also. I don't have a microphone, unfortunately, so go ahead.
Hi, thank you very much. First, nothing know about what I look from CSRO. I totally agree with the optimism in the last slide about the future for structural biology.
We don't hear you.
Sorry. My question is, how much of what you presented do you think is also translatable to cryo-EM, and how we can use, if you think that we will be able to use also in a similar way for solving cryo-EM structures?
Yeah, so the question was, first he agreed with the optimism of the last slide, and then does cryo-EM and X-ray, are they going to have similar uses of AlphaFold models? Is that right? And I think it's equal. In cryo-EM, X-ray, tomography, and any new things, NMR also for sure, and any new techniques that people use, is going to be extremely powerful. And actually, it's not even limited to the high resolution kind of structures. You know, spectroscopists, I haven't talked to anybody actually about doing it, but you know, they're using it for sure. You know, using these models as well to try to interpret their data, because why not? And once again, AlphaFold gives you these confidence measures. You can know which parts are likely to be telling you something. Then you can compare those parts to your experiment. Why not? So yes, I'm optimistic about all these things. Optimistic about the improvement of the prediction technology. Optimistic about the use of these in experiment. And you know, in 30 years, okay, the experiment may go away. I'm not even sure about that though. You know, it was funny. Like 25 years ago, we started structural genomics, right? Some of you guys know about this stuff. And in structural genomics, the big idea was we're going to solve enough structures so that we would know everything, right? And, you know, we didn't solve enough structures to know everything, of course. And I had this slide. It was a 50-year slide. The 50-year slide was, you know, we're going to know everything, and we're going to have the the physics to go with it, and we'll just be able to say what a cell does. And that was 50 years from then. It's 50 years from now, right? So, yeah.
It's fantastic, actually. And when we started ESI in 2000, that's exactly what we were promising.
Yes.
We'll be able to get a lot of this now. Now, can you push it a little bit further? I mean, more than what you actually described. Because the final structure is not always what the gene codes for. So let's say the simplest case, let's say nucleus and protein. Which structure are you predicting? Or, you know, some complexes that mature and you have to keep proteins and, you know, bind ligands, cofactors, others.
Yeah, Andre, it's a really good point. That right now we're so happy that these AI methods can predict something that looks like what we might be depositing in. It's great, right? But that's not what we really want, right? We want the structure of this thing in this environment, or this version of this thing, this covalently modified version of this thing, or whatever. And the thing is, so AlphaFold got really far very fast because of the PDB, right? Because there's this structured database that has all this information in it, that's highly redundant, that is highly comprehensive, and so it was able to interpret all that information and then make predictions about what a structure is likely to look like. The next level is a lot harder. So ligands is the next obvious level. Like, what ligand binds where in what protein, right? And actually, so DeepMind has made a new company to do exactly that, right? So they're working on it, and I'm sure they're going to do as good a job as can be done, because they joined up with a bunch of pharmaceutical companies, and they're all going to try to do this. They're going to pool their data. But the thing is, there isn't enough data to do that nearly as well as there is for proteins. So proteins has a limited number of interactions, limited number of components. Ligands has a huge number of components, a huge number of interactions to learn. It may work, and that's the right thing to do. So that's the next thing, is to have enormous databases of ligands to go ahead and try to predict how ligands are going. And then similarly for multiple conformations, similar for other conformational, conformations and modifications, covalent modifications. Yeah, so great point, Andre.
You combine cryo-EM and AlphaFold, X-ray and AlphaFold. As you begin to do quantitative microscopy and do subtomogram from structures inside the cell, when will we be able to combine AlphaFold, cryo-EM data, X-ray crystallography data, and put them all together to get the best out of the incellular structures that we
Yeah, that's what you want to do, all right. That's certainly where we want to go. It may take a little bit of time to do that, but definitely we and other people are thinking about that and would like to do exactly what you're saying, to combine all sources of information about a particular system and to try to make a comprehensive system that understands it and can predict as much as possible of it with guided by experiment. So that's definitely where everybody's going. Yes?
Okay, I have a microphone now, so.
Thank you, Diane. And thank you, Tom. That was awesome. But back to 2023. I'm interested in how dynamic the relationship is between AlphaFold predictions and the PDB. So I first thought of this when you said, okay, we took 200 structures that were deposited after the method, the AlphaFold method was published. So how do you know those aren't part of the AI that's now being used? That's part one. And then part two is, I know you can do an AlphaFold prediction without templating to the PDB. So is that, if you come with a sequence that maybe has homologs that, long back we would have made a homology model, yada, yada, but that's always biased towards the deposited structure, is an AlphaFold prediction in absence of the PDB a better model than a templated structure?
Yeah, so a lot of great questions, Janet. So AlphaFold, as Janet said, can predict using just multiple sequence alignment or using templates from the PDB or both. In fact, those predictions end up being very similar. And in fact, predictions with templates from the PDB are not any better, tiny bit, marginally better than templates not using any templates from the PDB. That AlphaFold people noted that in one of their addendums or one of their supplementary data. So basically, you get a different answer, slightly different answer. And in some cases, prediction with a template's better, and, from the PDB is better, and sometimes it's worse. So that one kind of answers that. You're kind of leading up to is there's a little bit circular, right? As we generate more structures, are we going to kind of make our structures look like something AlphaFold wants or something like that by using AlphaFold? You're not worried about that. Okay, well, I am. But other people are. Let me just dismiss it then. It's a straw man, okay, just for a moment then. So you might worry that AlphaFold prediction is going to go into the structures go in the PDB, use that PDB to generate new AlphaFold parameters, and then you're going to build something in wrong, right? And so I say don't worry about that very much because we have the experimental data, right? And so as long as we're working with high-resolution structures, and as long as next generations of AlphaFold prediction are trained with structures that are of high quality, namely generally high resolution, filtered for B factor, that kind of thing, those structures are all going to be good because they're going to be based on the experimental data. Anything that AlphaFold generates that's not right is going to get thrown out in that process, so that there isn't any circularity. So even though you weren't worried about that one, I guess. Yeah, okay.
Not at all. Is it dynamic?
And is it dynamic? At the moment, it's not dynamic.
Okay.
The parameters we're using are the original parameters, for example. There are some new... What?
Your experiment was valid.
I think so. Yes, that was valid. But, other people are, yeah. So the DeepMind team made new sets of parameters for multiple chains, for example. So that's a new one. But the original parameters are basically there. And then another team, the OpenFold team, is making has made a version of AlphaFold that's rewritten completely, different programming language, everything, but is fully trainable by them and by anybody. So anybody could take this, do whatever you want with it. And so there will be, over the next few years, many totally retrained systems so that it could become completely dynamic. Just to expand on that one more level, there is no reason why you can't take the PDB as it is today and then use it as each one as a template with experimental data, make a better model with AlphaFold, basically, and then make a new version of the PDB, and then use that iteratively to generate the whole thing. And there's no reason you can't do that. It's just a big job. I'm sure we're not the only ones thinking about doing that kind of thing. So, yeah.
Thank you so much for your nice presentation. Here.
I'm sorry, where are we? Oh, yeah. Hi.
Recently, we solved two structure with the AlphaFold model with high resolution data. During that time, I noticed that all the template model is generated by using one PDB structure based on the AlphaFold. But is there any idea to generate the AlphaFold model using multi-threading mode like ITOSR with the two different structure for generating the homology model for the M?
So I didn't quite get it, but I think you're asking, can you use multiple templates?
Yeah, for the one AlphaFold model.
To generate one AlphaFold model. Yeah, you can do that. You can actually supply as many templates as you want. And if you wanted to supply templates with different confirmations, you could do that too.
Okay, if it is possible, how much it will be the confidence score which you showed in the slides? How much it should be? It's above 90 or?
That would depend on the case. I don't know the answer to that one.
Thank you so much.
Yeah.